If you were with us for our last deep dive, you'll remember we took a close look at the circular economy. We talked all about the importance of redesigning what we make, creating products that are built to last, to be repaired, and to be recycled. But, that's really only half the battle. Because having a brilliant circular product design is one thing, but if you're still making it in a traditional, wasteful factory, well, you haven't closed the loop. To truly bring those products to life, you need a completely new kind of factory.
And this quote right here, it just hits the nail on the head. It's the perfect entry point into today's topic, the green factory. Now, I want you to get that old image of a factory out of your head. The loud, dirty, smoke-belching industrial plants of the 20th century. What we're talking about today is a world away from that. It's a place where advanced automation, artificial intelligence, and deep sustainability principles all converge. It's clean, it's quiet, it's incredibly intelligent, and it's hyper-efficient. This is where the future is being built. So the big question is, how does it all actually work?
Okay, so here's our game plan. We're going to break this whole concept down into 4 key pillars that really hold the whole structure up. First, we'll look at decarbonizing motion. How do we power the very machines that do the work? Then, we'll dive into manufacturing without waste. After that, we'll explore how these facilities achieve peak optimization. And finally, we'll tackle what might be the biggest challenge of all, creating a new material world by reinventing the very stuff our world is made of.
All right, let's dive right into our first pillar, decarbonizing motion. You see, traditional factories are absolute energy hogs. They are incredibly thirsty for power. So, the first and most fundamental question we have to answer is this. How do we possibly solve the massive energy consumption problem that exists on almost every factory floor in the world?
Well, the answer really begins with a fundamental shift in how we power automation itself. For decades, factories ran on compressed air, or pneumatics, and hydraulic fluid. And these systems are, to put it mildly, notoriously inefficient. Think about it. A pneumatic system needs a massive compressor running constantly 24/7 just to maintain pressure in the lines. It's always leaking, always losing energy as heat. It's like trying to keep a giant leaky balloon inflated all day long. The new paradigm completely scraps that. It's all electric, built around high-efficiency servo motors. The genius here is that they are direct drive and only consume significant power at the precise moment they are doing work. It's the difference between leaving a light on in an empty room all day long versus a smart, motion-activated light that only turns on when you walk in.
And the best part is that the efficiency gains are layered on top of each other. The servo motors are just the beginning. Modern robotic arms now incorporate regenerative braking. And if you've ever driven an electric vehicle, you know exactly what this is. When the robot arm slows down, instead of that kinetic energy being wasted as heat in a brake pad, it's captured, converted back into electricity, and fed back into the system. This creates this absolutely brilliant virtuous cycle. Engineers use advanced materials like carbon fiber and lightweight alloys to build the arms. Because the arm is lighter, it needs a smaller, more efficient motor to move it. And a smaller motor uses less energy to begin with, and then it still gets to recapture energy through regenerative braking. It's a beautiful feedback loop of savings.
Okay, so the hardware is incredibly smart, but the real magic, the quantum leap in efficiency, happens in the software, the brains behind the brawn. Every single time a factory makes a defective part, that's not just wasted material, it's a huge amount of wasted energy. Every stamp, every weld, every movement, all for nothing. Modern robots, with their breathtaking precision, we're talking sub-millimeter accuracy, slash those defect rates. Then you add AI-powered vision systems that act as tireless quality control inspectors, catching tiny errors in real time before another ounce of energy is wasted on a doomed part. And finally, you have intelligent motion planning. You can think of this as an AI ballet choreographer for robots. It analyzes every task and calculates the most fluid, most direct, most energy-efficient path for every single movement. Over millions of cycles, eliminating those tiny inefficiencies adds up to an absolutely staggering amount of saved energy.
So we've made the movement of the machines incredibly efficient, but that's just one piece of the puzzle, right? What about the materials they're working with? This brings us to our second pillar. How do we fundamentally shift away from manufacturing processes that create waste by their very design and move toward a world where we build things, well, almost atom by atom?
For basically all of human history, we've been masters of subtractive manufacturing. Think of a sculptor like Michelangelo with a giant block of marble. He starts with a huge block and then chips, cuts, and grinds away everything that isn't the statue of David. It's a masterpiece, of course, but it also creates a massive pile of wasted marble dust and chips. That's how we've always made things. We take a block of steel or a sheet of aluminum and we cut away what we don't want.
Additive manufacturing, which you probably know as 3D printing, completely flips that entire script on its head. Instead of starting with a block and removing material, you start with nothing. And you build the object up one microscopic layer at a time, using only the exact amount of material you need right where you need it. And the impact of this shift is just staggering. I want you to let this number sink in for a moment. For a complex aerospace part made of titanium, traditional CNC milling can turn up to 90% of that initial, very expensive, very energy-intensive block of titanium into scrap metal chips. 90%. Imagine buying 10 pounds of a precious material and throwing 9 pounds of it straight into the recycling bin. That's the old way. With additive methods, that waste can plummet to less than 10%. This is the crucial point. We're no longer just trying to reduce waste. We are fundamentally designing waste out of the process from the very beginning.
Now, this new way of building doesn't just save material, it unlocks entirely new worlds of design that were literally impossible before. This is where generative AI comes in. An engineer can tell the AI, okay, I need a part that can withstand this much force, connect at these points, and weigh as little as possible. The AI then runs through thousands, even millions of design permutations, often creating these complex, organic, almost alien-looking structures that look more like bone or honeycomb than something man-made. It's biomimicry on steroids. The AI has learned from nature that these are the most efficient ways to build strong, lightweight structures, putting material only where it's absolutely essential for structural integrity.
And if you're thinking this all sounds like futuristic stuff for spaceships and concept cars, think again. This technology might already be on your feet. A perfect real-world example is the Adidas Futurecraft 4D running shoe. It uses this exact combination of additive manufacturing and AI-driven design to completely transform how a simple shoe is made.
The entire midsole of that shoe is a 3D printed lattice. Now that lattice isn't just for looks. It's precisely tuned to provide cushioning and support exactly where an individual runner needs it based on their gait. That's a level of customization that's impossible with traditional foam molding, which involves cutting shapes from a big sheet of foam and creating a lot of scrap. This additive process creates far less waste. But more importantly, it points to a future of on-demand, localized manufacturing. Imagine walking into a store, getting your feet scanned, and having a pair of shoes with a perfectly customized midsole printed for you, right there. And it even opens the door for a truly circular product, a shoe made from a single, easily recyclable polymer that can be ground up and used to print the next pair.
Okay, so we're using less energy for every movement, we're using way less material for every part. We are definitely on a roll. But what happens when you zoom out? When you stop looking at individual robots and individual parts, and you look at the entire factory as a single living organism? How do you push that entire system to its absolute peak of resource efficiency? That brings us to our third pillar.
And this is where we encounter the concept of the lights-out factory. Now, when people hear this term, they often jump to conclusions about jobs and automation, and that is a very important and valid conversation to have. But for our discussion today, I want to focus on a different, profound implication: radical resource conservation. A lights-out factory is a facility so automated it can run for days or even weeks with literally no people inside. So what happens when you design a factory purely for the machines, with zero consideration for human comfort?
Well, the savings are immediate and massive. Just think about any large building you've been in. A huge chunk of its energy bill is just for the people inside. You need to light up a massive space, you need to run the HVAC system constantly, heating it in the winter, cooling it in the summer. It's a colossal energy drain. Robots, they couldn't care less. They can operate in the pitch black, they can operate in freezing cold or intense heat. By simply eliminating these human-centric systems, a dark factory can slash its baseline energy consumption by 20–30% or even more, right off the top. It's some of the lowest hanging fruit for energy savings, but on an industrial scale.
And this is where it gets really, really clever. Because it can run 24/7, a lights-out factory can become an intelligent partner with a wider energy grid. The factory's central AI is always monitoring the price and carbon intensity of electricity. When it sees a huge surge of wind power in the grid at 2 a.m., making electricity cheap and green, it can automatically ramp up the most energy-intensive processes. It's essentially bargain hunting for the cheapest, cleanest electrons. This isn't theoretical. The Japanese robotics giant Fanuc has been doing this for years. They have factories that run completely unsupervised for up to 30 days at a time, where the only thing happening inside is robots building more robots. It's a self-replicating, hyper-efficient ecosystem.
Okay, this leads us to our final, and you could argue our most critical pillar. Let's imagine we've built the perfect factory. It's got energy-sipping robots, it uses additive manufacturing, it's a lights-out facility that optimizes its energy use every second. That's fantastic. But what if the raw materials we are feeding into this perfect machine, the steel, the concrete, the plastics, have a massive embedded carbon footprint from their own creation? It's kind of like building the world's most efficient Tesla factory, but powering it with a coal plant. You haven't solved the core problem. We have to green the very building blocks of our industrial world.
And to understand the scale of this challenge, we have to start with the two undisputed titans of industry, steel and concrete. They are the bedrock of our civilization, and together they are responsible for a truly staggering 16% of all global CO2 emissions. Let me put that in perspective for you. That is more than the entire global transportation sector combined. All the cars, all the trucks, all the ships, all the planes. Steel and concrete are a bigger problem. So to be blunt, if we do not fix steel and concrete, we cannot build a sustainable world, period.
So, how do we do it? Let's start with steel. For centuries, making steel has meant one thing: blasting iron ore with incredible heat using coking coal. It's a carbon-intensive, dirty process. The revolution is to break that addiction to coal. There are two main pathways emerging. The first is to replace coal in the chemical reaction with green hydrogen. When you do that, the only byproduct, the only thing coming out of the smokestack, is water vapor. It's mind-blowing. The other path is to lean into the circular economy. Instead of digging up new iron ore, we use massive electric arc furnaces, powered entirely by renewables, to melt down and recycle the billions of tons of scrap steel we already have in the world.
Now, for concrete, which is the most widely used substance on Earth after water, there's an equally brilliant solution from innovators like CarbonCure. The process is it's elegant. You take CO2, the very greenhouse gas that's the problem, and you capture it from another industrial source. Then you inject that captured CO2 into a batch of fresh concrete as it's being mixed. Through a chemical reaction, the CO2 mineralizes. It literally turns into rock, becoming a permanent part of the concrete structure locked away forever. And here's the kicker, the absolute genius of it. This process actually makes the concrete stronger. You are taking a waste product, a pollutant, and turning it into a value-added performance enhancer. It's a perfect circle.
So how do you actually bring all of these complex ideas together to build a real green factory? Well, companies like Siemens are pioneering the answer with platforms that allow you to build the factory twice. First, you build it virtually. They call it a digital twin. It's a complete, dynamic, one-to-one virtual model of the entire facility living inside a computer. Using this twin, you can simulate a year's worth of operations in just a few hours. You can test every process, optimize every material flow, and hunt down every single point of wasted energy, all before you've laid a single brick or poured a yard of concrete. It's about achieving perfection in the digital world so that the factory is born efficient in the real world.
So let's just quickly bring it all home and recap those 4 pillars we talked about. First, it's about energy-efficient automation, using smart electric systems to do more work with far less energy. Second, it's additive manufacturing, changing our entire philosophy to design waste out from the very beginning. Third, it's about achieving peak resource optimization, using AI and concepts like the lights-out factory to squeeze every drop of efficiency out of the system. And finally, and most importantly, it's about building this entire new industrial revolution on a foundation of low-carbon materials.
You know, for so long there was this accepted wisdom that there was a trade-off. You could either be productive and profitable, or you could be sustainable and green. The Green Factory completely and utterly shatters that false choice. What we're seeing now is that these two goals are no longer in conflict. In fact, they have become two sides of the very same coin. Intelligent automation, when it's guided by these sustainable principles, shows us that the most efficient, the most productive, and ultimately the most profitable way to make things is also the most sustainable way. It's not just about making things faster anymore. It's about making them fundamentally better for everyone and for the planet. This whole idea of systemic change is a huge topic, and it connects directly into what we'll be exploring next time. So I really hope you'll join us as we dive into clean mobility, the journey to zero emissions transport. Thank you so much for watching. If you enjoyed this, please subscribe, like, and share, and don't forget to hit the bell for more from tech, AI, and beyond.